Yes,
Yes,
ma'am.
ma'am.
Okay. Yeah, so we'll start off formally on this class today. And okay, I want to be recording this meeting, right? Yeah. So, yes, you all can keep your videos off right now. Even I'll be switching off my video so as to conserve bandwidth. And one more information, that is that in case there is a power outage at this end, so my laptop is the only one which connects to the university ID. So in case that happens, in that case, I'll switch on into the other backup meet, which I can access through my phone. Okay. Yeah. As long as you've had that. Let me stay on this mode itself because it's easier to work through this. Is this screen visible to you?
Yes, ma'am.
Can you read whatever is written here?
Ma'am, could you zoom in a little bit?
Not clearly, ma'am.
Tell me which size is okay for you. So I'll keep it at that size. Is this
Ma'am, why
okay?
don't you maximize it at the top?
Huh?
You can maximize it at the top.
I didn't get it. You'll have to probably write
Maximize
it.
the window. Maximize the PowerPoint window.
This I'm doing it in PowerPoint so that I can kind of use my ink tablet also on it. That's the only reason why I'm doing it here. Had it been PDF, so that's not an issue. But in PDF, then I can write on that. So that's the main issue.
Ma'am,
Okay.
he's telling to maximize the window.
Oh, maximize the window. See that. Yeah, that is only because some people might still be entering. So, which is why I need to kind of keep it there. Okay, I'll try and keep it at the maximum. No issues. Okay, this is legible for you?
Yes, ma'am.
Yes, ma'am.
Okay. So, yeah. So, we are starting off with circuit theory. And as you know, the basic thing that we are going to deal with are currents and voltages and how to handle them, how to kind of write equations using in the electrical circuits, electrical or electronic circuits. So the major components in that's essentially currents. The first major component is current. And current, as you know, can be denoted as dq. Okay. Yeah. So that is which is visible again. Okay, this must be visible. I hope my pointer is visible, right?
Yes, ma'am.
Yes, ma'am.
So the current, it is dq by dt, and that is denoted by I. If you note here, this quantity q is in small and this I is also in small. That has a particular notation of its own, and the reason why we use it, I'll mention that slightly later. So this rate of change of charge with time. The moment I say rate, I'm assuming that it is with respect to time that I'm talking of. So it's a time-dependent variable. Charge is changing with respect to time, and that rate of change is denoted as the current. And you might have a capital notation or a small notation. As I said, I'll talk about these in more detail later. Units is typically amperes, and or in short form capital A itself. And whenever you've got any circuit line or something, it is essential, and I say it is essential to use this marking. This is absolutely, the direction of current must be put in very properly. This absolutely is essential. Okay. Without that, either you put it on this itself. So this has an absolutely different implication from whether if you are doing it this way. Okay. So these are not the same. Right. So you must be careful about that, and you must not miss out on the direction of current being denoted in a particular circuit. That keeps it incomplete. Charge, when it is transferred between T0 and T, so that is the integral of naturally the current. So integral T0 to T I dt, that is nothing but Q of T minus of Q of T0. Okay, so it's a lumped variable in that sense. Total charge transferred over all time, initial value at T0 plus whatever is the integral of the current over that particular duration of time. So that's a Q. And again, because the direction is important, so if I'm stating in this particular direction, so if I'm showing it in this direction effectively, that is 3 amperes, and if the current direction is shown to be the reverse in the opposite direction, then the sign also changes. The associated sign also changes. So sign change with respect to current simply means that the direction of current flow has changed. That means the positive and negative terminals in the circuit have kind of reversed. Okay. And again, one more thing, that is that you can give the direction separately on top, or as I'm marking here, directly on the circuit element itself, or on the wire or the connection itself. Types of currents that we normally talk of. The first one is DC. Second one is usually AC. So DC means direct current. AC means alternating current. Okay. And direct current, typically, these axes are time, and this is the current axis, so in amperes. So this would typically be in seconds, milliseconds, or whatever time units be. So in DC, what we are expecting is that the value is fairly constant. It may not be exactly just a fixed value, but it's fairly constant. AC, alternating current, that means the current is alternating with respect to time. That means your current value is switching from the positive domain. This is typically 0 of the current. So it is changing sign. So some portion it is in the positive direction, the other portion it's in the negative direction. Okay, that means the current in this particular line, that is toggling in one half cycle, as we say it. So in a one half cycle, it is flowing in a positive direction or in this direction. In the other half cycle, it's flowing in the reverse direction. So the value is going from positive to the negative, back to the positive, and so on and so forth. So that is why it is called alternating current. Again, as you know already, I presume that it's fairly it is typically you could denote it by a sinusoid. So A sine omega t would be a kind of representation for the particular circuit. So say I would be equal to some I naught sine of omega t. So this would be the sinusoid representation, where this would be the base value or the nominal value, and this would be the sinusoidal variation. This would be the angular frequency. Okay. Or else it could be in the AC itself, you could have a sinusoidal representation, or an exponential representation, or what is more common, quite common, a damped sinusoid representation. Okay, so if it's a sinusoid representation, it is this one. If it's an exponential representation, it is this. If it's an exponential current, exponential currents, or this we also call this is
But ma'am, in the exponential current, the direction is not changing, no?
no, the direction is not changing, but the rate of change is very large, which is why it is an alternating current in that particular, and it's not a direct current. Okay, so yeah, exponential current, we usually keep it under the group of AC currents itself, because it does not usually happen just by itself. Could be part of the DC also, actually. You have it as a transient effect. I'm just talking about that. So the transient, this happens usually during the transients. So say there is a step change in the input, either in the input voltage or the input current, whatever be the input to the particular circuit. Due to that, there are exponential currents which get generated due to that change. You know about inductances or capacitances. So if you are withdrawing or switching off or switching on inductances or capacitances in a circuit, in that case you have the exponential currents coming in, transient, which last for a very small duration of time typically, and typically the current would go down to zero. Okay, so it is not in that sense truly a direct current per se, because it's dying out to zero, and in that sense we call this a part of the AC current group or something. More usual is a damped sinusoid. So a damped sinusoid, when we look at that, that's actually a combination of this and this. So if you look at this, this is actually so there would actually be a exponential envelope as we talk of it. We'll deal with this more details when you're looking at RC circuits, RLC circuits, and so on. So there is a exponential your envelope, and in that you have the sinusoidal variation. So that being so, it forms the damped sinusoid. You note that this is the damped sinusoid when we are talking of. So this is again current that we are talking of here. So when we say damped sinusoid, or we say talk about the exponential, we are typically talking about the values dying out to zero. Why do you think that is so? Can it not be that the current looks something like would this be possible?
Energy conservation violation.
No,
Huh?
And not possible.
Why not possible? What would happen?
Because in the previous in damped sinusoid, energy is lost, but we can't gain energy just from outside without.
No, I have not said anything about the rest of the circuit. In a circuit, due to some reason, is it possible to have something like this? A current increasing.
Yes, ma'am, it is possible.
What would happen in that particular circuit? If that
possible. Short
Ma'am,
circuit.
current will increase to a particular limit and then it will not increase or it will decrease then.
it will then automatically?
Decrease or like become constant.
Oh, really? Why so?
Ma'am, after some time, ma'am, it will have tend to have infinite current. Means it's like short circuit.
Oh, you're saying it very smoothly and very sort of damping it down a lot. If this scenario happens, then there'll be a huge burst. If it is heavy machinery that you're talking of, it'll just blow. The current is increasing and rapidly so, and to a high value.
There will be a huge generation of heat, so it will ultimately burn out us.
Listen, talking about heat generation and all, you're kind of just sort of cloaking it very beautifully. Simple enough, there'll be a huge blast or a huge blow.
Ma'am, I wanted to say boom actually, but then I thought
Yes,
it won't
you should have
convenient.
said that. There is no harm in saying that. There will be a huge bloom. Okay, so which is why this is a scenario which we do not want. Right?
But ma'am, we see this type of graph in the forward bias, reverse bias in the diode.
Forward biased in the diode, that's a different scenario altogether. This I'm talking about an exponential rise per se, where
That
there
is
is
I
simply
versus B.
I drew an exponential like a reverse exponent, right? Dying out to zero. But what if this just kept on increasing? In a reverse bias diode, there is automatically a saturation. So it will never go exponential ad infinitum. It is only to some approximation that you can approximate it by this.
Yes, obviously there is an upper
In
bound.
a diode scenario. Okay, that's an approximation. That is not the actual total response of the diode. Fine. And even in the breakdown, if breakdown zone also, avalanche breakdown, if that goes on too high, so you have particular diodes which operate in the avalanche breakdown mode. Typically, if the same thing were to happen in any normal diode, the diode would burst. Okay, so capacitors burst, diodes burst, resistances burst, and yes, associated with that, whoever said that, you have lots of heat and maybe light and sound being generated depending on what's bursting. Okay, and maybe smoke also, all that. So this is the practical part of it. So this is what we have in the particular scenario for just for the current. Now, if you think of any circuit per se, a circuit, what do we call as a circuit? A circuit is actually a system. And what is it composed of? It may be composed of several elements. Okay, and these several elements that we are talking of, I've marked it out here, through which current flows when a voltage is applied across it. Okay, and I want to highlight out these two particular points. That is that voltage is applied. Sorry. So voltage is applied across in a circuit, while the current flows through a circuit. Okay, and we have the notion of, in general, in any particular physical system representation, you have these notions of through variables and across variables. Okay, so as you can understand that in electrical circuits, through variable is current, across variable is voltage. Okay, you apply voltage across two terminals, and if there is a closed path, then a current flows through it. Right? Can you tell me what would be a through variable and across variable in a mechanical system? Say a linear displacement system, mass spring damper.
Tension is across.
Tension is across. Okay.
And potential and force.
Come on. In where are you getting potential in a mass spring damper system? What did you want to say? You said force also. For what do you want to say with respect to force?
The spring constant is across. Spring constant. Okay.
Well, force across and tension through.
Force is across.
And tension is through.
Spring constant, you are not right in that. Yeah. And
tension is through.
Tension is through.
Energy across and displacement through.
Hey. energy. Had energy been across, then do you think an electrical circuit does not have energy?
Yes, ma'am.
So voltage is across, current is through. What is energy? Energy is equal to V is voltage, I is current. Energy E is equal to, you know this one.
VI.
VI.
VI is energy.
VIT. T
VI
for
is,
time.
VI is power.
VI is
Integral
power.
VI dt. Yeah, VI is power, so integral VI dt is your energy, right? So energy is neither a through variable nor an across variable. It must have a through variable and an across variable in it, right? Are you getting that? Here, I wrote it here also.
Yes, ma'am.
Fine. So energy is this, or in other words, it is integral V into I dt. So it will have both the components. So if it is
And
true
should
for
it be
electrical
displacement?
circuits, it will be true for the mechanical circuit also. Energy is energy.
I mean,
In
say force
whichever
and
system.
displacement.
Force and displacement. Yes. So now which is through and which is across?
Across is force and displacement is through.
Yes. So across is force. Okay. And when you're talking about the through variable, so that is the displacement. That is in one of the representations. You can have the reverse representation also. So, but like variable matching wise, you apply a force, or if you say tension, so you apply a force or a tensile force or a tension across an element, mechanical element, and due to that, there is a displacement that occurs in the elements. So that is a through variable. Okay. Now, so just like we talked about the current in terms of I and dq by dt. So similarly, if you're looking at voltage, so voltage is applied across two terminals. So voltage is applied across two terminals, plus minus. And here again, it is important to put in the signs. These are important. Okay. So if you are talking about the DC, then it is plus minus directly. If you are talking of AC, then you must indicate that it's an alternating voltage. Okay. So that must be indicated. Now, so that being so, voltage, this is known as voltage, and you would have the representation as a small v or a capital V. I'll again come to the notation small or large when how used, why so. Units are volts, representation capital V. Okay, capital A, capital V, primarily because these are names of physicists that we have, volta and ampere. So and as we were talking about it, the energy or the work done. So the work required to move the charge through the element, that is Q into V. So you have both the variables. Q is nothing but integral I dt. So as a result, this is also a through variable. Okay. So you have energy is nothing but work done, or energy is nothing but a composite of a through variable and an across variable. Okay. Now, what is power? In electrical circuits, or rather in engineering sciences, since it's an application science and electrical mainly, unlike in physics, when we are talking about power, we are talking about power absorbed. Okay, not power delivered, but power absorbed. By convention, power absorbed is positive. Okay, so how much is the power absorbed by any circuit element in terms of the voltage across it and the current through it, denoted by capital P or small p, as the case might be, units watts, capital W. And so as you see here, so now we have the, earlier on we were representing we were looking at simply the voltage, so we had not marked out the current. In order to talk about the moment we are talking about power, so obviously we are assuming that there is a closed path when if you're considering these two terminals also connected. So voltage applied across this, so a current, and there must be a direction of current noted, either directly on this itself or separately on top, whichever way it is. And it's understood that if it is going in through this, so it's coming out through this one. So this is the positive and the negative terminal. Else you could also have shown it on this one. In this case, the value would have been minus of whatever this value is. Okay. So as I mentioned, passive sign convention, so power or energy absorbed is considered to be positive. Now, so if we move on into, so a few more basic terms. First is the classification in terms of the current and voltage. Classification of elements in that. I mentioned that you talked about the spring constant being a true variable or something. A spring constant is actually sort of equivalent to, in that particular paradigm, it is equivalent to a resistance, or rather a conductance. Okay. So as a result, it functions, spring constant functions as a element, passive element in that particular context. We'll come to that later. So coming on to sources first. Sources, there are two types of sources that we are talking about: independent sources and dependent sources. When we say independent sources, that means whether it's a voltage or a current source, it could be a voltage source or an independent current source. So the voltage of the particular source is totally independent of the current it supplies. Okay. If it's an independent current source, then we should be able to say that the current which the source supplies is totally independent of the voltage that is being drawn from that particular element, from that particular source. Okay. Unless and until that is so, we cannot really call it an independent source. So in the truest sense, there is no practical source which is ideally independent. It can be independent over certain ranges of values. So for example, if just now we talked of the avalanche diode. So if you are thinking of the avalanche diode is typically operating in the reverse biased mode. And there you have the sharp rise in the current at a fixed voltage. So that particular element is capable of delivering a fixed voltage irrespective of the amount of current that is drawn through that at that particular value. So that then qualifies as an independent voltage source for that particular avalanche voltage value. Okay, that's one example. Obviously, a battery is an independent voltage source. For currents, yeah, I do have one thing listed out here. Anybody can tell me a independent current source? Independent voltage source is relatively easier to find. You have them whenever you're thinking of sources, you are mainly thinking about voltage sources. Anybody can tell me about a current source? Yeah. Oh, I did not switch off my video unnecessarily. Yeah. Anybody? I would like a response. Yes, no.
Solar panels.
Solar. Do you have current available? No, you again have voltages. You have supply in the voltage. So yes, current is generated, but then it is finally stored in a voltage in a battery, and then the battery supplies voltage. So when you're thinking of it as a source, it is a battery source effectively. Solar cell battery, right? Anything else? Anybody can think of something else?
Ma'am, diode at the saturation point, after the saturation point.
Diode after saturation, yes, you might think of it that way, because yeah, a fixed value of current irrespective of the voltage being drawn from there. It cannot supply more. Yes, you might think of it that way. Yes, not bad. Okay,
Ma'am,
fine.
generator.
Huh?
Ma'am, field effect transistors.
Generator.
Generators are typically voltage generators. Yeah, FETs. FETs again, it would depend upon the particular region of operation.
The saturation region.
Yes, so it would be just the basic transistor or the FET. It would be kind of the same group of elements, right? Yeah. Okay. Coming on to one more example here, which you see I've listed out here. So that is this proton beam of a cyclotron. Okay. So cyclotron, you have the proton beam that is generated, and proton beam, so it's just protons. So this is typically charge elements, positive charge elements, unit positive charge elements. So operating at constant beam currents, typical beam currents would be of the order of microamps or so. Okay. And in case your batch is interested, remember that it is possible to arrange a visit to VECC, which is quite close to the campus actually. We have organized trips, student trips to the VECC to see the cyclotron and its operation and all that. Okay. You have seniors also who do their, some seniors coming in from VECC for their master's courses in our department. So, and right now one of them is working with me for a PhD project, PhD topic on cyclotrons itself, automatic tuning of cyclotrons. Okay, now, so coming back to this one, so that is about independent sources, voltage sources and current sources. But usually most sources, practical sources, are dependent or controlled sources. So the source voltage of the current depends on the current or voltage elsewhere in the circuit. You could have those also. Right? So when you're talking about that, this again is a very specific case where the dependency is exactly must be known, otherwise it's no good. So this is what happens in a transistor when you're looking at the sort of the output side, or the from the you have the base and you have the collector or emitter currents. So emitter or collector currents, they are dependent on the base voltage or current. Okay, so the biasing voltage also decides that. So as a result, you have the representation, in the representation that the current source on the right hand side, that is actually a dependent source. Okay, so you have this one, and then you have this there. Okay, and you would have whatever. So this one is actually the dependent source, which decides by the current at this side. Okay, so that decides this one. Now, so independent voltage source representation. So it's understood that we are talking about ideal independent voltage sources, and typical representation for a DC voltage source, it would be 6 volts. You would denote the terminals in that. Current supplied by the source should be denoted, and the direction must be specified. Okay, so one depiction is like this, in a circle with the plus and minus terminals indicated, or else it could also be, it's a battery, DC battery, typical representation might also be like this, with the positive and negative electrodes being represented. Yeah. Now look at this. This is the household electrical outlets. These approximate an independent voltage source, 220 volts as we know. Okay, so 220 volts is the RMS voltage. So as a result, the maximum voltage, or actual the voltage profile, is actually 220 root 2, and sinusoidal variation, so cosine 50 hertz frequency, so 2 pi into 50 times t. So this is the actual representation of the voltage. Okay, so when we say 220 volts 50 hertz, so this actually encapsulates this much of information in it. that it is 220 root 2 is the maximum voltage available, and it's a cosine variation or a sinusoidal variation with 50 hertz frequency. So that is omega is 2 pi into 50 into time, and that's a voltage. So V is that as a units is a must. So if you have this, these are, as you know, that the fuses are attached to these outlets. Okay, so if you have a high voltage, high amperage outlet, in that case you would have a limit up to say 10 amps typically. So maximum you could draw instantaneously would be kind of about 20 or so. Fine. So for currents less than that, otherwise the normal other outlets you would have 5 amp fuses connected, so that would be about 7.5 to 8 amperes max that you could pull out instantaneously on that. So those are the ranges, but that can be treated as an independent voltage source. Independent current source, on the other hand, just like this was represented by this, so independent current source, you have to specify the direction, typically denoted within a circle itself. These are, as I mentioned, this was the transistor and also used in electronic circuits. They are more common in electronic circuits. Dependent sources, when we are looking at that, just a moment. Yeah, sorry. So dependent sources, when you're looking at that, so this would be the representation. So independent sources are circles. Dependent sources, these are typically diamond representations. So when you see a diamond like this, you would say, oh, my bad here. I did a wrong representation here. So let me just remove this. So it would actually be this one. Okay. So let me just correct it off here. So this is the kind of scenario that would have in transistor representations.
Ma'am, I had a question.
Yeah?
Ma'am, you said that independent.
I can't hear you.
Ma'am,
your voice is very low.
ma'am, you said that.
Who's it speaking, please? Orals. Hello?
Hello, ma'am.
I really can't hear you. Try again.
Ma'am, it's his problem.
Okay. So in since I can't hear you, would you write it up here on the chat box? So I'll read that up then. Okay, that works equally. So just write in your comment on this one. I'll read it up once it comes up. Right. So continuing till he writes in his comment. So this would be about the transistor representation. I was sorry for my mistake in representing possibly by this using the independent current notation. Okay. Now coming on to sources. So you have another representation. So this is about dependent, independent, dependent sources. Another is active elements and passive elements. So this is not just about sources, about all circuit elements. So obviously the sources are, sorry, yeah. So the sources are nothing but active elements. Why are those active elements? Because they are capable of delivering power to some external device. Okay, so those are active elements. Passive elements just absorb power. Okay. Now you are aware of electrical circuits. What are the passive elements?
Resistors.
RLC.
R, L, and C. Okay. So L and C, R is okay. R is purely passive. L and C, do they not deliver power?
Yes, ma'am.
Yes, ma'am.
But then why are they not called active elements?
Ma'am, they basically store power and then dissipate it afterwards. Ma'am, they don't generate power.
Exactly. So that is important. So as a result, in the passive elements definition, if you just look into the text there, I think I've not copied it out here. So if you look into the text there, what it says is that that the definition of an active element, this is capable of delivering power and over a large interval of time. Okay. So if there is some element which can deliver power locally over a short duration of time, over a finite duration of short finite duration of time, in that case it would qualify as a passive element in order to cater to the LNC elements also being passive elements. Okay, so that is how the definition is configured there. Now coming on to the notations, the capital and small notations. So this actually I have taken from Millman and Halkias. There's a electronics text. The chapter in that is transistor at low frequencies. I've forgotten the exact name of the text also. We just refer to it usually as Millman Halkias. So in the chapter in transistor at low frequencies, you will find that there's a table given there, and that denotes all these. So let's just go through this once. So the instantaneous total value, whatever is the instantaneous, that means occurring at a particular instant of time, and the total value, whether of a voltage or of a current, voltage V, current I. So since it is the instantaneous value, you have small v or small I. Because it is the total value, hence you have the capital V in both the cases. So this is actually for the transistors. So naturally base is what they're talking about. The quiescent value or the nominal value. I could also write of it as the nominal value. Quite often we refer to this as the nominal value in other representations. So that quiescent value is both capital V or I and capital B. So that is essentially the DC bias level of the voltage or current in that particular circuit or in that particular part of the circuit. Okay. The instantaneous value of a varying component. This was the total component. Total component, so this was capital. The moment it's a varying component, so this becomes small. So this is small v, small I, and these are also small b. So this is essentially this minus this. This is the bias level. If you subtract out the bias level from the total instantaneous total value, you have the instantaneous varying component. Okay. Effective value, or what we also denote as the RMS. RMS value, if we are talking about that. That is denoted by, so effective value is actually a fixed value that we state. So hence, it is a capital V or a capital I, but it is the effective value of a varying component. So this subscript is now small. Okay. While this is true for electronics circuits itself, not applicable in the electrical circuits that we'll be talking about here. We'll actually not even be talking about these subscripts in this particular electrical circuits text. Okay. But this is just that you're aware of the nuances of the capitals and smalls and all of them. So supply voltage, when you're looking at that, so that is denoted by capital V, because its supply voltage is typically a DC voltage that you provide, on top of which there is the variation, the AC variation, which we use either for the gain or so on and so forth for various purposes. Okay, so that is capital V, and typical notation is double subscript. Okay, VCC, VBB, so that way. So this is about the notation. Coming on to the passive element, the first passive element, and how we deal with that. So the basic element, as you are already aware of, resistive element or resistance, and Ohm's law, as it defines, Ohm's law defines the linear resistor. So what this says is voltage across many types of conducting materials is directly proportional to the current flowing through the material. Okay, and that proportionality constant R is nothing but the proportionality constant. Okay, so because V is proportional to I in these type of conducting materials, so as long as this proportionality holds, the proportionality constant is known as R. So R is the constant of proportionality, which is known as the property of the element, which is the resistance. Units ohms, as you're aware of, and that is nothing but volts per amps, 1 volt per amp. Okay, representation typical, this one, and please note again current and voltage. There's one more thing that I want you to note here, that is that power absorbed convention. So please note this one, that is the power absorbed convention. So when you're looking at that, so the current enters the positive terminal. Okay, so I in this direction, it's positive, into this V value, which is positive at this end. So V into I, positive into positive. So power absorbed is V into I. Okay, had this current direction or this value been negative, that means the current direction would have been reversed. What I'm saying is, you would have two other scenarios. Current entering here, sorry, yeah, so this is minus and this is plus. This could be that. So this would be power absorbed would become minus VI. That means power is effectively delivered across this element. Or rather, it simply implies that the actual current flowing is in this direction, in the reverse direction, not this. So that would then be the positive with respect to that and the negative. I'm unnecessarily overcorrecting myself. Yeah. So this would be the implication of that. Okay. So that would then be through this direction, it would again be a positive VI, which was the power absorbed, but in this direction now. Okay. So typically when we are talking about Ohm's law, I went into power absorbed. So let's come back into the element itself. So if you're looking at the graph of voltage versus current, or rather, yeah, actually, yeah. Okay, so in this particular graph, I've drawn voltage on the y-axis and current on the x-axis. And since it's a linear resistor, so the variation here is linear. Typically, however, whenever we have characteristics of elements that we draw, it is usually V on this axis and I on this axis. Can anybody tell me why? This would again be a linear, sorry. Yeah, there will still be a linear representation. Anybody?
Current is the dependent variable depending upon the voltage.
Yeah, usually you have voltage sources. Okay, so since we are talking about voltage sources, so voltage is the independent variable with respect to which current is generated. So as a result, this would be the typical IV characteristics that you have of materials that you will see in several of the curves. However, this one was voltage to current. So naturally, the slope in this one would be nothing but 1 by R. It's a linear curve, so 1 by R. In a transistor, you have seen that you were talking about instantaneous slopes because the curve was not linear. So as a result, you were talking about instantaneous slopes. So that means in a transistor and in a diode, is Ohm's law valid?
No, ma'am.
It is not valid. So please understand that. Okay. So Ohm's law is actually a basic law, and which says that conducting materials, many types of conducting materials, This is one thing. And if you look at the proper definition there, actually this constant, this is proportional to the current flowing through the material under normal operating temperatures and other, provided that temperature and other environmental conditions remain constant. That is there in the definition. Okay, so it is essential that those conditions are maintained constant, because unless and until those conditions are maintained constant, you know that if there is a wire, if that is heated, will the resistance across the wire remain the same?
No, ma'am.
What is the relation there?
It will increase with temperature.
R is equal to?
R
Rho L
plus
by A.
alpha T.
1 plus R into 1 plus alpha T.
Alpha T.
Delta T. Delta
Actually,
T.
delta T.
Delta
Okay.
T.
Yeah. Right. So this is the typical relation for in heated wire. Right. So which is why it is important that you have the representation is there, provided temperature and other environmental conditions, humidity or anything else which might be secondary factors which might affect the particular material. So those have to be kept constant. Okay. Oh, I think I wrote it here also. Yeah. See, I wrote it here. So provided temperature and other environmental factors are held constant for certain ranges of, and so this is true for certain ranges of current, voltage and power. It cannot be true of any particular. You supply any resistance. So you supply it with any high value of current. Would you still have Ohm's law valid? Yes, no, what do you think? Can you supply any value of current through any resistor?
No, ma'am, it will burn out.
Yes, it will burn out. Okay. Thanks for providing the burnout. Yeah, and so what we actually have ratings of the resistances. Any of these passive elements, you have ratings. So in the ratings, you will have the value of the particular resistance or the inductance or the voltage limit or something. Along with that, there will be a power rating also. How much power can that element tolerate? Okay, or absorb. So how much heating can that tolerate? So that is the indication of that. So that must, the power rating must be, so usual, the anybody has an idea as to what is the power rating of the usual lab resistances? You have worked with the resistances in the labs, right?
And we have not been to the labs.
No, not here, but in your schools and colleges, you must have used resistances in labs.
Ma'am, 5 volt.
Power rating, I'm talking about power rating, so.
Oh, power rating, no.
It's never with resistance. What is stated? It's a what is the typical color coding for resistances? Do you know that?
And the digits and the multiplier and the tolerance.
Yes, ma'am, we know that.
So what is the typical mnemonic that you have for that?
B.B. Roy from Great Britain has a very good wife.
Yes, exactly.
Given
So that is the mnemonic. So you would look at the color coding there, and you would know that what is the, how much ohms is that particular resistance, right? And you would look at the silver or gold or whatever, you would know the amount of tolerance in that. So apart from that, there is a power rating of that particular resistance. Any of these elements will have a power rating, as I'm stating. How much is the power rating usually of these lab resistances?
25 watts.
20?
5
25 watt?
watts.
What's
Watts.
the watts? 25 watts. No.
Nearly 1 watt.
These are actually quarter watt or half watt kind of elements. Okay. So as low as that. Yeah. So coming back to this one. So actual resistors. Oh, by the way, resistance values are normally positive quantities. Negative resistances can be generated or can be rather simulated with special circuitry. Okay, so negative resistances per se do not exist. So they have to be simulated separately in case there is a specific utility of that. Actual resistors are nonlinear. Special examples, as we were already talking about, avalanche diodes, Zener diodes, tunnel diodes, fuses. So those are nonlinear resistors per se. Absorbed power is dissipated as heat, and which is always positive. No power delivering capacity or storing capacity, and the power is typically V into I. And since the relation is V is equal to Ri, so you can just substitute that here, and so you have this is equal to I square R, or otherwise V square by R. You're aware of this. As I was mentioning, that wattage is essential. So this is 100 ohms 2 watt carbon resistor across 110 volt source. Okay, so if you connect that, so this is the V, this is the amount of, so V square by R, if you calculate, that exceeds this value, so naturally you will have a burnout. Okay, now coming on to the next part of it. Now the other representation, instead of talking about only about resistances, we do talk about conductances also. So conductance is nothing but inverse of the resistance, 1 by R. Okay, so as a result, your relation is I by V, and units are just more ohm in reverse. So this is ohm in reverse, so it is mho, MHO, and this also you just reverse from this one, just topple it down, so this becomes a mho. Or nowadays the unit Siemens is also used, so capital S, in terms by the name of the German scientist. Now we have the absorbed power. Accordingly, this becomes V of I, and I is now V into G, so this is I square by G. So V square times G, or I square by G. What you had typically there as V square by R, if you were talking in terms of resistance, and that was square into R. So it's R replaced by 1 by G in all the cases. These, whenever we are talking about these, the most common content that we'll be talking about are the instantaneous values. So all of these representations I've been writing in terms of the instantaneous values itself, because it is the instantaneous changes which are most critical whenever you're analyzing or you're observing any particular circuit. You will look at total values or quiescent values, but overall at one go at some point of time. But while you're monitoring a system, or while you're asking for some performance out of a system, you would be interested in the instantaneous values that are delivered there. Now, so you're looking at the current through or the voltage across the resistor, which are varying with time in some manner. Okay. Now, typically, if you've got a sinusoidal voltage, say V is equal to 2 sine 100t times of V, and R is a fixed value, 10 ohms. So obviously, your I is equal to V by R. Just a moment. Yeah. Udbhash writes, Madam, you said independent current source. Oh, that was that. How can we fit a huge cyclotron? Oh, no. Udbhash, that was one example of a independent current source. The cyclotron proton beam as an independent current source is actually one of the closest to the ideal independent current source. Okay, but in an electronic circuit, I corrected myself later. That is that I drew that representation for mistakenly. It is actually a dependent current source on the secondary side or on the output side of the transistor. Okay. Just so to clarify back, let me just go back once, a slide or two. Yeah, so this is what I was talking about in the transistor representation. I think you're aware of this also, the hybrid representation or the hybrid mode representation. Udvash, is that so? Does this answer your question? You could write it off.
Yes, ma'am. Yes, ma'am.
Okay, fine. Yeah. Now, so coming back to this one. So, yeah. So when you're looking at the current here, that is V by R. So you've got typically, naturally, just the quiescent value, and the sinusoidal variation remains the same because this does not have, this is a fixed element, no sinusoidal variation per se in that. And if you're talking about the power, it is V square by R or I square into R. So that would work out as this. Now look at what's happening here. There's something that's interesting happening here. What is the frequency in the current or the voltage signals? Angular frequency. Let's talk about angular frequency. Yeah, please, once again.
It's 100.
100.
100.
Simple. Right. Look at the power. What is the angular frequency here?
Same.
It's the same. And here, this is where I miss being in a physical classroom, you know, because had I been in a physical classroom, I would have simply asked you people to put up your hands and seen how many are going which way.
Oh, it's sine square. Sorry, ma'am.
It's a sine square. So anybody with any other answer?
And the frequency is doubled.
Frequency is double. Okay. So wait, let me just write out the options here. Yeah, I do have space at the bottom here. Okay. So what you've all said is, so one group says 100. I'm talking about the power thing. Everybody agrees that voltage and current frequency is 100. Angular frequency is 100, right?
Yes, ma'am.
Okay. So this is for the power. Power, frequency, angular. Yeah. So one answer is 100. Second answer is double. So that means 200. Any other answers?
I'm half.
Half. 50. Any others? I should have something to have a poll on something, na?
Ma'am, 0.
0? You must be joking.
Just joking. Yes, ma'am.
Okay. So I'll keep the joke aside. So I'll cancel this one out. Fine. So you stay restricted between these three. Now, how do I get a vote on this one? Anybody with an idea of how to go about a voting on these three options?
Now you have to create a poll separately.
Or you can call out everyone's name and ask
No.
them.
That will be too time taking. Just for this one, it's not worth it. Okay. Okay. Let's have a reasoning for that. Anybody provide me with a reasoning for all of these three separate answers? The ones with the 100. Why do you say it's 100? That's simple enough. Yeah? Anybody? Or anybody wants to justify as to why you are stating this or that? Any of these?
Ma'am, in a sine square graph, the like the area under, like the negative area gets flipped to the positive area, so the frequency of the full wave becomes the frequency of the half wave, so the frequency in some ways doubles, ma'am.
Frequency as a result doubles. Okay, that was Shuddha Shattu, right?
Yes, ma'am.
Okay.
Ma'am,
So,
we can
fine.
use trigonometric ratios to convert sine square theta into cos 2 theta, and then we can say the angular frequency is double.
Okay, so this is Ovirup.
Yes, ma'am.
Angular frequency is double.
Yes, ma'am.
Oh,
Ma'am,
so
it's 200.
you and Shuddha Shattu are on the same page.
Yes, ma'am.
Okay, fine. Yeah. The person who said half? 100, I'm assuming that because I can see 100 here, so you're saying 100. Yeah. In the meantime, I'm drawing curves, so don't worry. Anybody wants to explain out why the 50 was there? Should have come down here itself. Anybody? Huh?
I'm 200.
200. Oh, so you've all zoned on to 200. So this answer has gone off. Who said 50 earlier? Who was it who? You want to remain at 50 or you want to change your answer?
Ma'am, he was suggesting the options only. He wasn't answering the question, I think.
Oh, okay. So just providing me with an option. Okay, that's not a bad idea. Okay. Anyway, this is right, as you see, because the time period is defined by when the signal starts repeating itself, right? So this would be typically the time period T of the voltage or the current signal, because it starts repeating itself. You can either take it from a zero crossing to the next to next zero crossing, or else from one maxima to the next maxima. Gives you the same duration. Okay, or from a minima to a minima. These are the easier points. It could actually be any other point also suitably mentioned, but this is how we normally talk about time periods. Okay, so the signal is repeating itself. So from one maxima, it's come on to the other maxima again, and again the same kind of waveform repeats, again comes up to a maximum. There's a single maxima in this particular kind of a waveform, sinusoidal. Same thing happens here. So here it is, the angular frequency is 1 by t, proportional to 1 by t, and that is equal to 100 here. Okay. While here what happens is, if you look from this maxima to this maxima, this is actually halved. Because this has halved, so the omega has become proportional to 2 by t. So this becomes 200. Okay. Or else, in other words, if you're looking at this sine square theta, then sine square theta is related to sine 2 theta as a component, right? Or rather, cos 2 theta. 1 minus cos 2 theta by 2. Right? So your theta changes to 2 theta. So here also you can understand from that representation also. Let me just clear this one off very dirty. So this is related to cos 2 theta. So as a result, your frequency doubles from the theta to the 2 theta. Okay? I hope it's okay with everybody. Yeah. Now, when we are talking of two extreme cases, short circuit or open circuit, in terms of resistance values, short circuit means resistance is 0. Open circuit means resistance is infinite. Okay. When you say a resistance is 0, that means V is equal to IR. So irrespective of the amount of current flowing through that circuit, you don't have any voltage being recorded across the circuit. Okay. So that's the short circuit condition. Open circuit, whatever be the voltage applied across that particular element, because it is open, there is no current flowing through the circuit. So current through the circuit is 0. It is an open circuit, so there is no closed path. These were small examples which are already worked out there. So yeah, V is -8. Okay. And I is equal to -5 milliamps. So naturally, R is equal to V by I. So that would be 1.60. So you end up still with a positive value there. Okay. Absorbed power, how much is the absorbed power? Is I is equal to this. I is a negative value. That means the current in the current direction should have been reversed. R is a positive value. And so since power is nothing but I square into R, so whether it be negative or positive, it does not really matter. This would be 25 into 2.2 or 50 into 5 into 11. So that's 55 volts. Okay. If you have, how much is the current? Power absorbed is given and R is given. So naturally you can find out I square and then take the square root. However, since it is current that you are determining, note that it is not possible to determine just from this expression itself as to the direction. What is the direction of the current in that particular circuit? It could be in one direction or it could be a reverse direction. Plus or minus simply indicates change of direction. V is given, I is given. So naturally it's possible to find out G as I by V. Okay. So that was about this. Coming on to the next component. So yeah. Yeah. Here we are going to talk about Kirchhoff's laws. Are you aware of Kirchhoff's laws?
Yes.
How many Kirchhoff laws are there?
KVL and KCL.
KVL and KCL. Okay. Anybody has any notion as to the Kirchhoff's laws and their relation to conservation laws?
Yes, ma'am.
KVL is based on conservation of energy and KCL is based on conservation of charge at a node.
Yes, absolutely so. Thank you. Yeah. Or KCL in that particular sense, you could also think of in the larger context, you could think of it as a conservation of momentum principle. Okay. So that's actually the through variable. So if you think of the through variable and the conservation law in terms of the through variable, so that is nothing but the conservation of momentum principle. Yeah. But it is essentially conservation of charge at a particular node that way. So Kirchhoff's laws are essentially conservation laws. And before we go on into Kirchhoff's laws, let me talk about this particular concept, that of lumped constants. Lumped constants, and here you have distributed constants. Okay. So these are very important, and I'm realizing it more and more due to as we do some research on piezo elements and so on and so forth for sensing purposes, for biomedical signal processing and stuff like that. So, and in doing so, naturally piezo elements, the thing is that piezoelectric elements, what they do is that they can convert electrical energy into mechanical vibrations, or if there are mechanical vibrations which are impinged on that particular system, you can get equivalent charge generated out of it. Okay, so that is it works both ways, reversibly so. So naturally, we are looking at relations where we are relating from electrical principles into mechanical principles also. So that paradigm. And in doing so, these concepts become very much more important, because in electrical theory, what we do is we mainly talk about lumped constant systems. Okay, while if you were to look at mechanical systems, or if you looked at furthermore, if you looked at thermal systems, okay, temperature variation in a, say, a heater of large length, or in a pipeline. So if you're thinking about that, so you would have a temperature profile or a heat conduction profile. Okay. Or if you're thinking of mechanical systems, as I said, spring constant, when we are talking of that, if there are small elements, then you can think of that as a single spring constant. If there are large elements, then there also you would be talking of integrals and sort of distributed constant networks. Say the moment of inertia, when you have calculated, you have looked at moment of inertia for large bodies or something, you have not been able to talk of a single value, but instead you have done integral dm kind of things. So localized mass elements and then integrals over them. Okay. So when you're looking at those kind of paradigms, that means you're looking at the distributed constant network kind of systems. Okay. So actual systems per se, you would actually have a distributed constant network. But in electrical, the concept has been there right from the beginning of treating systems as perfectly conducting. So this is the concept, that of perfectly conducting systems. Okay, so the lumpedness is actually courtesy this approximation, that the system can be considered to be perfectly conducting. So as a result, I can lump the total resistance of the system, or the total inductance of the system, or the total capacitance of the system effectively at one point. However large be my motor, I can state it to have a single particular fixed resistance. I don't need to say integral something Rm dm. I don't need to integrate the or have a resistance profile for that particular motor element, or an inductance profile of a particular coil, or a capacitive profile of two large capacitor plates. Capacitors, at times we do use distributed constant networks, but most often we will still be talking about lumped single capacitor values. Okay, and that gives rise to a whole set of analysis which is simple, elegant, and at the same time allows you to get a feel of what is happening in the system. Then if you need so, you might go in for a deeper second approximation towards the, you can extend it to the distributed constant network if the requirement so increases. Okay, so I just expanded it a bit out because this is usually something not very much discussed, and why you would be using lumped constant or distributed constant. So just wanted you to have a feel of why we do that. This
Hello,
will, yes.
Ma'am, can't we say the lumped system is the approximation of Maxwell equations, so that we can get the KCL and the KVL kind of laws?
See, the KCL and the KVL kind of laws are actually very simple. Those are just conservation laws. And those, because we have considered lumped constants, as a result, they become very simple.
And they are very simple because we take the approximation of Maxwell equations. If we go for the direct derivation of Kirchhoff's laws and stuff, we will end up in the Maxwell equations.
Yeah, I agree. But had you, what you are saying in essence is, had you started with the distributed constant representation, then it would have been a much more complicated thing, which you would have approximated down to a KVL or a KCL.
Yes, ma'am.
Okay. So instead of doing that, what people have done in electrical is they've directly taken the approximation in the representation itself. Instead of a distributed constant representation, we normally talk of a lumped constant representation itself. And as a result, we have the simple KCL and the KVL that we directly talk of. Okay?
Okay, ma'am. Okay, ma'am. Thank you.
Yes, and what I was adding on to this point is that why this is important is because the production regime that you people will be going into, now we are talking about nanomaterials, MEMS or electromechanical systems, small devices, battery sizes have really come down. Okay, your ICs, you have even more dense packed ICs, and ICs are integrated circuits, so dense packed ICs and all. So electronics are more of a way to go. Large mechanical systems are giving way. In fact, even for automobiles and all, earlier on, you used to have the cranks, the shafts and the cranks and so on and so forth. Those systems itself are changing into the electrical motors and so on and so forth. The powering mechanism is also changing. Okay. So the heat generation is being reduced so as to make it more efficient and green, because clean energy is a requirement. So that way also electrical helps. Fine. And the moment you're doing that, so you will be negotiating this lumped parameter, distributed constant parameter representations a lot more than what even we have in our generation. I consider myself as almost a spent generation. I'm just here to kind of mentor you, and you will go on into the applications, which hopefully I'll be able to see to some extent that, yeah, my students are coming up with things interesting as this. Okay, so hence my 2 cents into this. Yeah, coming on to the standard definition. So standard definitions, please understand that we will be all over talking of lumped constant networks itself, or lumped parameter representations itself. In electrical, we usually do not talk of distributed parameter representations. Okay, and that works out actually to a lot of advantage. Coming on to analysis, before we get onto the KVL or the KCL, there are a few definitions here. So the first definition is that of node. A node is a point at which 2 or more elements have a common connection. Okay, so as you can see here, there are 3 nodes. Okay, yeah. Now tell me one thing. Just voice out, whoever voices out first. How many branches connecting at 1? How many at 2? How many at 3? Simple question. It's just a count.
Ma'am, 4 at 1, 2 at 3, and 4 at 2.
Yeah, and please see that in this, you have 4 at 1, out of which 1 is a source. Okay, so it is irrespective of whether it's a source or a passive element. That has nothing to do with whether it can be called a node or whatever. Right? As long as you have elements being connected there, it's good enough. Now, when we go into this one, here, this representation, please understand that there are still just 3 nodes, not 4. Why so? Because there is no passive element or no active or passive element connected between these 2. And our approximation is perfectly conducting. Right? So since that is the approximation, so as a result, this is still node 1 itself. Okay? This does not count. This wire is considered to be perfectly conducting. So whether this point or this point, it is actually the same point. Hence, it is the same node. Okay? And that is what is one of the first advantages of using a lumped network. Had it been a distributed network, this kind of a connection, I should have considered that, okay, there is a resistance in the wire. Length of the wire is this much. Hence, I should consider that also. Hence, this will be one node, this will be another node. This will be a node with plus delta R due to this amount of wire coming in. Okay? Am I making myself clear?
Ma'am, so these two circuits are like equivalent, right?
Yeah, these two circuits are equivalent. Because we are considering lumped networks. Okay? And why are they equivalent? Because we have considered in the lumped network, lumped parameter understanding, we have considered that wires are perfectly conducting. Okay? Now, in practice, what happens? Let me now take you into practice. In the lab, there is one thing to be sort of careful of as and when you get to the lab and start actually fiddling with stuff with the hands. So the length of the wire that you're connecting between two elements makes a difference in your results because of this approximation, of this assumption.
Yes, ma'am.
Can you repeat the same? Sorry.
What I said is that if you are connecting, say you've got two elements, say one element here and another element here, and you are connecting them with wires. In one case, you have attached this length of wire. Okay. On the other side, you have attached, say, I needed a different color of a pen. Anyway, let me go on with this. Which is better? This one or this one? Which connection is preferable?
B.
B.
Obviously B. Why so?
Length is less.
Length of the wire has been reduced. Why so again? Because
Ma'am, because the wires are
is
not
going to be
perfectly
violated. Get it? I can hear a lot of answers coming in. Good for me. Okay, good for you also. Because this is exactly like if you look back into your theory, you're violating this assumption more and more as you go in for longer wires. So naturally, your results are going to start differing because this actually has some delta R associated with this, which I'm discounting. This is an R1, this is an R2. Same. Okay, and maybe I was taking a connection out from here. Okay. So whether I'm connecting this way or I'm connecting this way makes a difference. Yeah. So that is about node. Coming on to a path. What is a path? Path is, it's a long description there. You start at one node in the network, go through an element to another node, through another element to a third node, and so on, without encountering, and this part is important, without encountering a node more than once. This is critical. Okay. So in this, if I'm traversing from here, I can go from here to here. Then I can go from here to here. Then through to this element. Then through to this element. Then from here, I can go back through this to here. Could I then go anywhere else from this one point?
I'm back to 2.
No, I couldn't because I have already counted this one once.
Would form a loop within itself.
See? So I would have to stop per se here. This would be the end of this particular path. Okay. If I started another path, say, here, and then I could have gone this way. Could I go anywhere else from here? No, I can't. Because I will again be crossing this 2 in order to go either here or here. Okay, so that is not allowed. So you start at one node in the network, through an element to another node, and so on. You can go on. As long as you are not encountering any particular node more than once. You can encounter a particular node only once. Or else you can go and stop there at max. You can't cross it again. So that is your rule for a path. Okay, closed path, if you start at a node and back to the node. So like, obviously, which of the two is a closed path? The red one or the black one?
Black one.
Black one is a closed path. We started at 2, ended at 1, or started at 1, ended at 1. Came to 2, ended at 1. Okay. Even if I had started this one also, from this point onwards, had I started at 1, come through a 3, to a 2, and back to 1, that would have been a closed path. Okay. Alternatively, if I thought of, say, starting from here and say I went this way, back to this would also be a closed path. Right? So those are the 3 definitions of a node, a path, and a more specific one, which is a closed path, or which is also called a loop. We use this definition quite a lot, loop. Particularly even in control theory also, you'll come to loop and loop gain and so on and so forth. So loop is nothing but a closed path. Oh, there is one more concept, that of a branch. Okay. If you have a single path, both ends being 2 nodes at either side of the element, then you have branches. Okay. So let me denote this one as S. This is node 1, this is node 3, this is node 2. Can you tell me the branches here? I've written down there are 5 branches. Can you specify out which are the branches from where to where?
2 branches between 1 and 2.
1 to 2 and 2 to 1. Let me just, in order to just differentiate. Yeah.
1 to 3, 3 to 2.
1 to 3,
3 to
3 to 2. Yeah.
2 to 1 again.
1 to 2 via the current source.
2 to
2 to 1.
2 to 1 via current source.
2 to 1. So 2S1.
Yes.
Right? This is not a node. So 2S1. Right. Yeah. So these are the 5 branches that you have. Okay. Good. Now, coming on to the Kirchhoff's current law. First, let's start off with the current law. So if we start off with the currents law, so algebraic sum of the currents entering any node is 0. As you mentioned correctly earlier itself, so you have essentially there is no accumulation of charges at any particular node. If you have a node, you don't have any charges accumulated. An analogy for this one is, whether you can appreciate this or not, if you think of a pipeline, there are joints in a pipeline, right? And you know of fountains also and everything where there are multiple connections connected to one particular node. So you can visualize a node in a pipeline where there are 2-3 branches branching off from that. Okay. So actually the notion of through and across came in from pipeline and hydraulic flow itself, or water flow. So if you think of that, at any particular node, you can never store any water in a particular node. It will always flow on into any one of the particular branches. Okay, so net storage of water in a particular node is 0. So net storage of charge in a particular circuit node is 0. In effect, so the net rate of change of the current, rate of change of the charge stored in that particular node is also 0. So the amount algebraic sum of the currents entering a node is 0. Okay, which I've mentioned here also, the charge cannot accumulate at any node. Right? So if this is a particular node, and these are, now directions specified. So IA and IB are entering this particular node. IC and ID are shown to be leaving that particular node. So since these are leaving, so current entering a particular node, power absorbed convention. So current entering is considered positive. Current leaving is considered to be negative. Okay. So that being so, IA plus IB minus IC minus ID is equal to 0. That's a reason for the minuses associated here. Okay. Or just a short script here. Summation n is equal to 1 to capital N, as many as the number of branches, capital N number of branches. Summation of I, N is equal to 0. Okay. This is for the power absorbed convention. Had it been the power delivered convention, then obviously these you would have treated as minuses, these you would have treated as pluses. So this overall equation would have been just be multiplied by a minus sign. So you would actually have minus of IA minus of IB plus of IC plus of ID is equal to 0. And that would still be the same relation. IA plus IB would still be equal to IC plus ID. Okay. And this is something that I mentioned earlier itself. So mass flow rate in a hydraulic system is equivalent to a charge flow rate or current in an electrical system. Very simply so. So that's the equivalence there. So through variable in a hydraulic flow system is equivalent to current is the mass flow rate. Okay. Now coming on to the KVL or the Kirchhoff's voltage law. Algebraic sum of voltages, this is around any closed path in a circuit is 0. So the energy, conservation of energy principle. So the energy required to move a charge from one point to another is independent of the path taken. That is what it means. And that is again thanks to the lumped parameter system and a time invariance that is considered. So this is also due to a time invariant system where you don't have lossless systems, time invariant systems. So you don't have any losses being considered. So as a result, conservation of energy holds. So as a result, irrespective of the path that you've taken, so the energy required to move a charge is independent of the path. Since that is so, so here we just have particular depictions of voltages, the terminals being marked. Okay. And here the understanding is that you assume there is a current flow in any particular direction. Let us consider that the current is flowing in this direction. Okay. So if the current is flowing in this direction, it encounters a minus sign here first. Okay. And this is the equation which becomes valid then. So it's a minus V1. Next, it encounters a plus here. So take that sign up, plus V2. Then it encounters a minus sign here, minus of V3. And you're back into this place. So the closed path total, okay, is equal to 0. Fine. Or in other words, it is V1 is equal to V2 minus V3. In this summation notation, this would again interpret to summation of Vn is equal to 0. Please understand that had I taken the reverse direction, say this as the direction of flow, for this one, the equation would have been nothing but, yeah, so I would have traversed from this direction. So plus of V3 minus of V2 plus of V1 is equal to 0. Okay. And effectively, you would have nothing but just the sign reversal of this one. So the relation would still have been the same. So V1 would still have been V2 minus V3. So that holds whichever way you consider it. But what is important is this is more of a practice technique that you follow systematically. You don't generally grasp at this, then this, then this. Don't jump about all about the place. If you're starting up from here, traverse the whole path systematically, and you will encounter all the elements. If you're starting up from here, traverse this one whole and go in properly, complete the path right of the equation. So you'll be okay. Okay? Don't just jump about here and there. So this was about it. How much do I have left? Okay. Yeah. It's actually quite close to 2 now. Yeah, so okay.
Ma'am, what is the difference between a loop and a mesh?
Loop and a mesh. Actually, a mesh is something that you can place out on a plane paper, on a two-dimensional plane. So that is a mesh. Okay. And yeah, meshes have some more limitations there, because one mesh you cannot have, a loop can have another loop inside it, but a mesh would be kind of independent of each other. Okay, so let me just look up here. For example, here, this is one loop, this is another loop, right? 2 through S to 1 is one, and 2 through this resistance back through the other is another loop. Okay, while 2 through S through 1 through this one, the second resistance as drawn here, would also be a loop, right? Who was it questioning?
Yes, ma'am.
Okay. Now, since I've laid it out on the paper in this way, so I would draw this one off, this one off as mesh 1, this one off as mesh 2, and this one off as mesh 3, without these crossing each other. But this could be one loop, this could also have been another loop. So if I were thinking of loops, I could have had this loop and I could have had this also as a loop. Am I making myself clear? Shomojit?
Means in a mesh we can consider only one time, right?
Meshes are kind of, yeah, the elements in a mesh, in 2 or 3 meshes, there is only one common element between 2 meshes. I shouldn't say one, I should specify as one. The overlap elements are not, the nodes would not repeat each other. So that way. Only be a pair reference and this one which will be common. I'll give you the formal definition by the next class. Mesh, actually, the moment we go into mesh analysis, we'll automatically be looking out at the meshes. Okay. Just yet again. Okay, let me draw it out here. How does it matter? What I'm saying is, I'm drawing the same thing. Just now pushing it out further. So this was the 3 point and this is this. So this is one mesh, this is another mesh, this is another mesh. 3 mesh currents. Okay. So it's just as laid out. So that way. Fine. You would normally not have this as a mesh. That would be a super mesh. Do you get it? Although this would still be a loop. What I was drawing was this one. This one would be a loop, but it would not qualify as a mesh. Okay?
Okay,
Hello?
that means we cannot bypass a node, right? The mesh.
Yeah.
Okay, ma'am.
And it is on a planar system. Loops are irrespective of whether it's on a planar diagram or 3-planar or multidimensional. Loops you can always identify. Okay. For mesh analysis, you have to be able to lay it out on a 2D plane. Otherwise, you cannot do a mesh analysis. That's a restriction. Okay? Yeah. I think today I'll stop at this point because there are simple things that I wanted to try out here. Yeah, these are actually nothing but problems that I wanted to be able to deal out with. Okay, in case we deal out with the theory the next day in time, then after that I'll take up these so that we can just kind of discuss it in class, so that you people get a feel of how it's going on. Otherwise, these are worked out example illustrated problems in the book itself, but just so you people can work it out yourselves, which is why I was interested in getting them done in class. Okay. By the way, just in this particular circuit, can you tell me the number of nodes and branches? This particular first circuit. How many nodes?
Ma'am, were you saying something?
Huh?
Were you saying something?
Yeah. I said how many nodes in this particular nodes and branches in this particular first circuit?
5.
5 nodes.
5 nodes. Can you tell me the points?
Ma'am, between the voltage source and the 6 ohm.
Wait, let me keep on marking. This is 1. Yeah.
Then just after the 6 ohm, that point.
Okay.
Then between RA and 5 current source.
Okay.
Then between RB and current source.
Yeah.
Then between that 3-point junction, ma'am, 6 ohm and RB.
Right. Okay. Fine. A number of branches?
6.
Which would be the branches?
Between 3 and 4, then between 2 and 3, between 5 and 4, between 5 and 1, between 5 and 2, and 1 and 2.
And 1 at?
1 and 2, ma'am.
1 and 2. Right. Yeah. So 5 nodes and 6 branches. Okay. So 1, 2, 3, 4, 5, and 6. Okay. What about this one? This is very simple. This problem issue is very simple. Yeah. How many?
4.
6 node.
Okay. Let's have the numberings out. Tell me locations.
Ma'am, in between 6 ampere and R1.
6 ampere and R1. Shall I mark it out here?
There.
Okay. Fine.
1. In between 5 ohm and R2, the central point.
How many nodes branches connected here?
3.
3.
Okay.
2. Then if we go down in between R2 and 5 ohm,
okay.
at that point 3, and in between R1 and 5 ohm.
R1 12 ampere and 5 ohm.
The 3 branch connection.
Again a 3 branch connection.
Only these.
Somebody said 6. Where are the other 2? Sorted out, whoever said 6. Hopefully, yes. Okay. How many branches?
1, 2, 3, 4, 5, 6.
6.
There were 6 branches which went on into the nodes. Okay, fine. So this would be 1, 2, 3, 4, 5, and this would be the 6, right? Okay.
Yes.
This is simple. How many nodes and nodes? Tell me the node locations. How many nodes and tell me the node locations.
Ma'am, I2 50 and 25 junction.
Uh,
Yes, ma'am, this one.
this one. This one is one. Okay.
And ma'am, the I2 25 150. This will be a single one junction at the bottom.
At the bottom.
Yes, ma'am.
Okay.
And ma'am, 50 100 and another 50. Yes, ma'am. This one.
Yeah.
Only three.
Yeah. So there are just these three here. And how many number of branches?
Yeah.
5.
2,
5
3,
branches.
4, 5.
1, 2, 3, 4, and 5, right? Okay. Yeah. And actually, I would have asked you to determine the Ix and the Vx in each of these cases. That simple Ohm's law that you'll be using and the KVL, KCL, right? Okay. Same here also. Yeah. And the power absorbed in each element. So those would be the doables. In case you do them, these are just the illustrated problems from the book itself. So in case you do them, so we can discuss it out right at the outset in the next class. Okay. So much for today. We'll continue on further for the next one. Yeah. Any other questions or anything? I can just take a question or two in case.
Ma'am, please send the notes to us.
The notes, they'll actually, it's from the book itself. And right now they'll be there in your presentation also. So you'll either get the link directly to that, or else I'll send it in the Google group. So you can connect to that. Okay. And this is nothing but the notes itself. I'm writing directly on the notes itself here.
Yes, ma'am.
Okay.
Hello, ma'am.
Yeah.
Ma'am, can you please explain the negative resistance again?
Which one?
Negative resistance.
Negative resistance.
Yes, ma'am.
Negative resistance, I won't exactly be talking about it. It's a simulation circuit that we make. So it's like the software circuit kind of a model that we make in order to get a negative resistance. It does not exist. Huh?
Ma'am, we can create a negative resistor practically.
Yes, it can be created. It can be created. But it's not a practical element per se. Like, you don't have it physically, a negative resistance does not exist.
Okay, ma'am. I will look into it.
You can yourself look it up on the net, or else I'll give you a link on that one.
Okay, ma'am. I will. Thank you, ma'am.
Yeah, okay. Thank you then for today.
Thank you, ma'am.
Thank you, ma'am.
Somebody is taking the